terminal potential difference. To make it crystal clear, I draw the diagram of internal resistance inside, which is not shown here, but you know already I've told you that internal resistance is always within the cell. So this is one cell having EMF E. Internal resistance is within this. Suppose this cell is having EMF E, current flowing through it. Once you say the current is I, it means through external resistance and it's also through internal resistance. Already you know this thing also, that because of internal resistance there is potential drop in it that always reduces the basic value of EMF of the cell. So effective EMF that is left to be out from the cell is only E minus IR. This is the EMF that will be out from the cell. Internal resistance, nobody is bothered, that is within it. So across the two terms, the net potential difference you are going to have it this much. This is known as terminal potential difference. It simply means that it is the potential difference between the two plates, two electrodes of this cell. But when we draw the diagram, normally we draw it outside. That's why a bit of confusion takes place, but that should be always made clear that terminal potential differences between the two terminals of the cell, two electrodes of the cell, or the two plates of the cell. Well, you compare this relation. First, you just modify this relation. This is Ri plus E. Then it becomes Y in X plus C. You draw the diagram. Along y-axis you are going to have V. Along x-axis you are going to have current. Then this angle suppose is theta. You know M is tan theta. And that is here equal to minus R. You might say this slope is equal to the internal resistance of the cell. At any point, you could choose any point anywhere. Suppose you have chosen this point, then above this is going to be IR, this will be V equal to E minus IR. You could say the other way also, that sum of these two parts is going to be equal to total EMF of the cell. You see, you have already known that the power produced will be different and power output will be different. Total power output is across the output resistance only. This is I square R. And total power produces this one. The ratio of the two, that is known as efficiency of the cell, because this is the only useful power that is being provided from the cell. This will be the output power. This ratio is going to be R upon R plus R. Since resistance can never be negative, certainly this denominator is going to be greater than capital R. So once you get the denominator greater than numerator, obviously the whole fraction is less than 1. We conclude ultimately that efficiency of any cell is always less than 1, that is 100%. Better to say with confidence that no cell could have the efficiency greater than 100% or even up to 100%. This is just impossible. For charging of cell, you see, you always need a DC source of higher EMF. Means charging is possible with DC source only. You want to charge this cell, you need another cell of higher voltage. So here we have shown one cell to be charged, the other the charging cell. The total EMF is going to be difference of the two, E dash minus C. Total resistance you want to know already, R plus R dash plus capital R. The current flowing through the circuit is going to be total EMF upon total resistance. It's written over here. This is the way to charge the cell. Remember, only secondary cells could be charged, not the primary.